Okay, let's quickly talk about what happens when we have a reciprocal function with a quadratic. So back this train up, and we know that with quadratic functions you can have either two x-intercepts, right, when you've got something that looks like this, or you can have one x-intercept with something that looks like, this. Man, I am the worst. Or no x-intercepts, which has something that looks like this. Now, let's think about what we know with reciprocals. The vertical asymptote is going to exist where the x-intercepts are. So if you have two x-intercepts, then you should have two vertical asymptotes, and your horizontal asymptote is still at 0. Oh, it's not at 2, but there are 2. Let's rewrite that. Okay, so if you only have one x-intercept, and actually let me go back, so you're gonna have a vertical asymptote here and here, right, at your x-intercepts. If you only have one x-intercept, then where can you have a vertical asymptote? You can only have one vertical asymptote. So you can have only one, and your horizontal asymptote's still going to exist at 0. Over here, when you have no x-intercepts, can you have a vertical asymptote? No, you cannot have one, but, you can still have a horizontal asymptote at 0. So let's look a little bit closer at what each of those mean generally. All right, so if you have two x-intercepts, so let's say we have something that is like y equals x squared plus, I should not do that, negative x minus 12. So if I'm going to take the reciprocal of this, it's going to be 1 over x squared minus x minus 12. And if I come look for my x-intercepts of my original function, I need to factor this, and I'm going to factor it to x minus 4 times x plus 3, and I'm going to find out that my x-intercepts are at 4, 0, and negative 3, 0. That means I'm also going to have vertical asymptotes when x is 4 and when x is negative 3, and I'm going to have a horizontal asymptote when where y is 0. So if I go to graph this thing, think about what we know. We know that if I graph my original function, and I'm like 1, 2, 3, 4, 1, 2, 3, my original function is going to be like this. Okay. And now I know my reciprocal function is going to have these vertical asymptotes that are right here, because those are the values that would create an undefined function. I also have a horizontal asymptote here. So my reciprocal function is going to only be in the region where the original function is. So kind of this top left, this bottom middle, and this top right. And my reciprocal function is going to go the opposite direction. So it's going to go like this, and it's going to be increasing where the original is decreasing. The original is opening up, so the reciprocal is going to open down. And this is increasing, so this is going to decrease. This also means that there are going to be 4 invariant points, 4 points of intersection. And they're all still occurring at 1 and negative 1. And to solve for those invariant points, there's a couple ways to do this, but you are going to have to replace that y with 1, and you're going to have to replace the y with negative 1, and then you're going to need to use, I would say you should use the quadratic formula. Now, I'm not going to spend our time here doing that, but I'll get you started. Remember, to use a quadratic formula, you need your y to be 0, which means this 1 needs to move over. So you're going to have x squared minus x, negative 12 minus 1 is negative 13. And on the other side, you have to do that too. So x squared minus x, negative 12 plus 1 is negative 11. So your like a value is 1, your b value is negative 1, your c is negative 13. And then you just solve for x, right? And that's going to give you, you're going to get 2 x values from this. And then you can just pair them with the y for 1 and find your invariant points. You can do that on your own though. All right, now let's talk about when we have one y-intercept. So let's say we have a function. This is our original function. It's x plus 2 squared. So the reciprocal of this is going to be 1 over x plus 2 squared. And we know that x plus 2 squared is a bounce, right? And it's over here at negative 2. So it's going to do this. So that negative 2 is also going to be undefined in the reciprocal. So I'm going to end up with a vertical asymptote here. I also, as x gets large, y is approaching 0. So I have a horizontal asymptote there as well. So now you can see that this kind of bottom region isn't being used at all by our original function, which means our reciprocal function has to be on top. So it's going to do the opposite of the original. So the original is decreasing, our reciprocal function is going to come in and increase, and it's going to just kind of hug the asymptotes, and it's going to do the same over here. Does that make sense? And how many invariant points do we have? We have 2 of them. I mean, like, you can just like look and count. There's 2 of them, and they can't possibly be at negative 1, right? They can only be at positive 1. So, all right, so our horizontal asymptote we realized is at negative 2. Our x-intercept was at negative 2. Our horizontal asymptote was at 0. And now our invariant points, we're going to say they're only at 1. So I'm going to replace my y with 1. X plus 2 squared. Now, to deal with that, I'm going to take the square root of both sides. And the square root of 1 is both positive 1 and negative 1. And the square root of x squared plus 2 squared is x plus 2. So I'm going to separate. And I'm going to say 1 equals x plus 2. And negative 1 equals x plus 2. So then I end up with negative 1 is x. And negative 3 is x. So therefore, my invariant points are going to be at negative 3, 1, because remember I used a 1 for this, and negative 1, 1. And sure enough, look up here, that's where they are. They're at negative 1, 1, and negative 3, 1. Okay, so that's what it looks like with just one vertical asymptote or one x-intercept on your parabola. Now when you've got none, let's say we've got like y equals x squared plus 3. So this has no y-intercept, or this has no, x-intercept. And if I just look at this, I know this is a vertical translation, and it's going to go up 3. So my original function is doing this, and it's opening up. Now, I have no x-intercept, which means I have no vertical asymptote. However, I still have a horizontal asymptote at 0. So that's still there because when I write my reciprocal function is 1 over x squared plus 3. And as x gets large, y is still approaching 0. So I still have a horizontal asymptote. So the way this is going to work is there's also no invariant points, which you'll see in a second. So I'm going to take the reciprocal. I don't know if you remember, but at the beginning we talked about how you could take the reciprocal of the vertex. So if this is at 2, what is 3? If this is 3. What is the reciprocal of 3? Well, it's a third, right? And if this is 4, what's the reciprocal of 4? Well, it's a fourth. And this is 4 too, and the reciprocal of 4 is a fourth. So our reciprocal function, if we make a table of values, is going to just kind of hug this, have this little bump or blip, and keep traveling along. Because think about it, as this is like, 8, this is it's going to be like 1/8. And as this is higher, in a 10, this is going to be a 10th. So this is just getting smaller and smaller. So the greater y gets, the smaller y gets here on your reciprocal function. Okay, so full recap. In quadratics, you have some options. If you've got 2 x-intercepts of the parabola, you've got 2 vertical asymptotes, 1 x-intercept on the parabola, 1 vertical asymptote, 0 x-intercepts, no vertical asymptote. 2 looks like this. Okay, this is what 2 looks like. You're going to most likely need the quadratic formula to solve for invariant points. 1 looks like this. It can be negative also. This one just happens to be positive. And no x-intercepts looks like this, and you get a blip. Okay, I hope that helps. You guys are the best. Bye.